Hi, my name is Preet Singh. I'm professor at the School of Material Science and Engineering. This is part one of two-part corrosion testing module. In these modules, I'm going to introduce you to high throughput methods for corrosion testing. We'll talk about fundamentals of the electrochemical methods for corrosion monitoring, introduce you to active passive state of metal, electrochemical method for measuring localized corrosion susceptibility, and we'll also introduce test methods for different forms of corrosion. So when we talk of corrosion rate measurement, if you think of corrosion, it may manifest itself into in number of years or months. So to measure mass loss over that time period accurately can take very long time. So one way of doing that is that you expose some metals, metal coupons, and measure their weight initially and afterwards, and by weight change you can actually find out what the mass loss was. But that is very time consuming. Whereas we have some non-destructive methods, especially electrochemical methods, which are fast and they can be measured to measure instantaneous corrosion rate. So these non-destructive electrochemical methods can be divided into two different method categories, direct current methods and alternating current methods. In direct current methods, again, there are two methods, TEFL extrapolation and polarization resistance, whereas in AC methods, we typically use electrochemical impedance spectroscopy to get corrosion rate measurements. Now, in previous module, I had introduced that corrosion rate can be related to current density, which is passing through the cell. Now, we're going to talk about how that can be done. So to do these experiments, you need typically a 3-electrode electrochemical cell, which has a working electrode, reference electrode, and counter electrode. So working electrode is the one which your alloy that you're trying to test. The counter electrode is some platinum or inert metal, and reference electrode is electrode which is typically like standard hydrogen electrode or calomel electrode, which does not change its potential during these measurements, or it works as a reference state. So to measure that, you typically need a voltmeter or a current source, or there are equipment which are available called potentiostats or galvanostats. So in this case, what you do is either control potential, apply potential and measure current, or you apply current and measure potential. So if you're applying current, it's called galvanostat. If you're applying potential, it's called potentiostat. You can use one electrode, or you can actually use multi-electrode array sensors. For example, here you can see that we have a number of electrodes embedded in the same electrode here, and each one of them is connected to a potentiostat or electrochemical cell, and they can be different alloys, giving you different cells. Instead of having different cells, you can actually do all these tests in a same setup. Now, to do this type of measurements, what we are really looking after or looking for is a corrosion current density, or I sub corr, which can be related to then corrosion rate. Now, problem is that we cannot measure corrosion I corr on its own. So because of that, what we need to do is actually extrapolate or polarize that state, so that we can do either by using potentiostat or a galvanostat. So we use polarization behavior of metal and then extrapolate it back to determine eye corrosion. There are two methods to determine eye corrosion, which can be then related to instantaneous corrosion rate. In one method, what you do is you measure potential or E corrosion, which is this value here, and once you have determined that, you polarize your metal to anodic side, which is going in positive direction, or cathodic side, which is going in negative direction, till you actually, if you plot current density or log of current density versus potential, till you reach that linear region on that plot, you actually polarize these metals, which can be many hundreds of millivolts from this corrosion potential. So once you have done that, you can do that either by controlling potential and measuring current, or you can actually apply current and measure potential. In either case, what you need to do is plot potential versus log of current density, and that can actually give you that linear region or TEFL region that you can then extrapolate. So that linear region can be extrapolated back to, if you extrapolate that linear region from cathodic and anodic TEFL slopes, where it intersects, that is your eye corrosion, and then eye corrosion can be related to corrosion rate. So that behavior, linear behavior, can be related where you can actually relate potential to the net applied current by using Butler-Volmer or TEFL type of equation. Now, as I mentioned, that the linear part is called TEFL slope, and just by plotting log of current or current density versus potential, you can not only determine eye corrosion, but also you can determine TEFL, anodic TEFL slope and cathodic TEFL slopes, and these can be directly put into this Butler-Volmer equation to find out eye corrosion, which is basically where the net anodic and cathodic currents are same or equal. So if we, once we have that eye corrosion, we can actually determine corrosion rate. The second method to do the same is called polarization resistance method. In this method, we don't have to polarize to hundreds of millivolts to get into TEFL slope. Instead of that, we polarize our working electrode only about 10 plus and minus volts from millivolts from E corrosion, and we plot current and not the log current density versus potential. So when you do that, when you plot your external current density versus potential, you get a linear part in this type of plot, and slope of that is called polarization resistance. So that polarization resistance now can be related to eye corrosion or corrosion current. So just by finding that slope of this type of relationship, you can find eye corrosion and use that in Faraday's equation to find out corrosion rate.